like trying to give you a face. Can you hear me? Dylan? Okay, how do you pronounce your last name? I just want to make sure I'm saying it the right way.
Yeah,
I don't know which way to...
Sorry, I couldn't find my unmute. Brout.
Okay. Brout.
Brout, like
Okay.
trout.
Okay, great, thank you.
I don't know if we had a paper schedule. Oh, yeah?
Oh, yeah, it's just be quicker.
Yeah, I'll check in a second.
Yeah.
This is different. This is my correct.
Yeah.
Oh, it works different than my Windows machine.
Uh-huh. Yeah. It even works differently than my Mac.
Yeah.
That look familiar? Okay. Nice. Open what?
Let's open a PDF. Just pick a PDF out of the presentations folder. Just to make sure it's open. You know.
Closing this.
Okay. Oh, okay. Oh, yeah. Okay. Then hopefully it'll be. Keynote or PDF or.
I don't know. Let me see.
Yeah, just skip. Probably a minute.
Well,
it's backwards.
She has a paper copy, or you're gonna?
Well, she took a picture of mine.
Oh,
it's
okay.
all good.
Okay,
She's
cool.
fine.
No.
Yeah, right there.
Okay, right.
That's keynote.
Oh, it's
okay,
not
we don't
alphabetical.
Need to open it. Yeah, you don't need to open it. It just. I was just looking to see if we had this. So they're all keynote.
Yeah.
Okay. Cool. Fine. All right. We need to have the blue jeans here though, so we can see when he's. Oh shit! I just closed it. Hit the wrong button. Okay. How do I get it back? Yes, I just killed the blue jeans thing. Wait here. Kevin. I need his help. Kevin? No, I don't know. They have to.
Oh, okay. No problem. No problem. Yeah, I left it open this time just in case that happened again. All right.
Thank you so much. All right. Minor freak out. Not minor freak out. Okay. That's what I wanted to do. Okay, good morning, everybody. Wow. Did we party a little too hard last night? Not even one good morning back. All right. Good morning, everybody. Good morning. Thank you. Okay, good. You're awake. All right. I'd like to introduce our first. Oh, wait, do we have any? Do you want the announcements real quick? Okay, the tour thing. Oh, you know what? Can we do it? We'll do it afterwards. Okay. We'll let people know what tours are going on today. Okay. Well, Kevin figures out what we're doing here. Cool. Introduce our first chair for the morning, Ariana Long, and take it away.
Morning, everybody. Our first talk today is Dylan Brout, 2019 Einstein Fellow. Dylan, I will give you a 2-minute warning. You also want a 5-minute warning?
No, 2 minutes is good. I have like a slide right around there. I can skip.
Okay, I'll just like pop in so don't be jarred when you hear.
No worries.
Okay. All right, take it away.
Thank you so much. Can you see my screen? I can't tell, but I'm going to... Okay. Thank you.
Yes, we can hear you.
Great. So for those of you I haven't met, my name's Dylan Brout. I regrettably can't make it to this. It sounds like there was some fun had last night, and I missed out on that. And I'm really glad to be here remotely to give this talk on something that I said I would do in my application, and I was really hoping I would do, and we did it. So I'm really excited to talk about the Pantheon Plus combined sample of 1550 Type 1a supernovae. So just kind of a brief history in the context of combined samples. I'll remind you that the Nobel Prize winning samples for the discovery of the accelerating universe actually combined pretty much 2 samples, one at low redshift and one at high redshift. That being because at low redshift, you need to cover lots of volume to catch the relatively rare Type 1a supernovae that go off in the very nearby universe. So you need to design a survey to catch those. And then at high redshift, you need to design a survey that drills deeper to get the more magnitude limited sample at much higher redshift. And so you focus on specific areas on the sky. And so you end up with sort of these 2 samples, one at low redshift, one at high redshift. And it's really the difference between the 2 that gives you the leverage on the cosmological model, as you can see here. And so for Pantheon Plus, we've combined many different samples over the last 25 years. And we've gone way back and used some old samples, largely because we want to include the supernova samples that include supernovae in Cepheid calibrator galaxies that are visible by the Hubble Space Telescope. So going back to 1995, it's taken 25 years to collect 42 supernovae. Now, the full Pantheon Plus compilation is 1,701 light curves of 1,550 unique Type 1a supernovae. So we have many light curves from different telescopes of the same supernova, which is really good for pinning down calibration uncertainties. And our sample goes from essentially redshift of 0 to redshift of 2.3, 3/4 of the way back to the Big Bang. And in order to do so, we've compiled 18 different surveys, 25 different photometric systems, and 105 different filters. And that means that we now have an average of 2 photometric systems for every supernova that is in a Cepheid host galaxy. So that's really important, again, for mitigating systematic uncertainties, especially for those Cepheid hosts. And so that means we have 80 light curves approximately of 42 supernovae in Cepheid hosts. So a quick reminder about the shoes analysis, which is now very much related to Pantheon Plus, but slightly different, where the shoes analysis deals with absolutely calibrated distances via the distance ladder. So just a quick reminder, the first rung of the distance ladder, you take absolute distances, for example, from parallax, and use those absolute distances to calibrate the Cepheid period luminosity relation. Those Cepheids, however, can only be seen out to redshift 0.01 roughly. So we transfer that calibration to the Type 1a supernovae in the second rung of the distance ladder. This is where we have 42. and it's one of the rate limiting steps. And then once we have that absolute calibration of the type 1a supernova, we can look out into the Hubble flow and measure H0, which is degenerate with the absolute calibration of type 1a supernovae. We can also measure other cosmological parameters, omega matter and W, and we do that in the Pantheon plus analysis. But the key thing I want to highlight is that now, for the SHOES analysis, the second and third rungs of the supernovae that are used are all coming from the Pantheon plus sample. So this was not the case in 2016. In the most recent analysis, this is now the case, and it's very important because it's the differences between the second and third rungs of the distance ladder that can introduce biases in H0. If both the second and third rungs, let's say all of your supernovae are off by 100 magnitudes, it'll come out in the calibration offset. But if there's a difference between the two rungs, then that's where you get the biases. And so we've taken great care to analyze both rungs simultaneously with the same pipelines and propagating systematics through both rungs simultaneously, and most importantly, characterizing uncertainties consistently and covariances amongst the rungs, systematic covariances. And when it comes to measuring H0, at this point, the name of the game is systematics, and that's what we've taken great care to keep track of through all the rungs of the distance ladder. We now essentially have this distance ladder covariance matrix to get the most robust possible uncertainties we can. And what it allows us to do is allows us to measure all of the nuisance parameters from the geometric distance measurements all the way through the Hubble flow and all the way out to redshift 2.3 and measuring our cosmology all simultaneously while including systematic uncertainties. And so this has been, when it comes to characterizing systematic uncertainties, a real effort over the last 3 years. And you've heard me talk about a number of these papers in my previous fellowship talks. I'm obviously not going to have time to go over these today. I want to highlight just a couple of the contributions of the earlier career scientists and one key paper that really has facilitated this analysis and this compilation, which is the Calibration Paper, where we've tied all 18 different surveys and 105 filters together using the Pan-STARRS All-Sky catalog, stellar catalog, which is a really great catalog which has great uniformity across the sky, which is important for tying all of the surveys together as they all have some overlap with Pan-STARRS. And what we do is we float all of the calibrations of all the surveys, including Pan-STARRS, this intermediary, and we put priors on each of the surveys based on how well they claim their calibration is done or how well we believe it. Some of the older ones, we've inflated their uncertainties. But what this amounts to is that we've essentially refined 105 of the filter 0 points. And with that solution, we retrain the supernova model, which we find is an important piece of the process for characterizing systematic uncertainties, and we report a covariance matrix. Because the Pan-STARRS All-Sky catalog is also allowed to float in the FIT, you get a covariance amongst all the survey 0 points, and we propagate that to cosmology. And when we do get to cosmology, after skipping lots of steps, we find W is consistent with -1. We find an omega matter slightly high, compared to other results, but not abnormally so, of 0.33. And we are now incorporating over 115 sources of systematic uncertainty. This data is either soon or already available in Cosmosis and Kabaya that's being put out as we speak. And we are actually not dominated by systematic uncertainties, which is really exciting for the future of supernova cosmology, even though we've gone through and incorporated every possible source of systematic that we can possibly think of. And when we compare it with the Planck results on omega matter and W, we find that in combination, they are actually very much consistent with the W of -1. Now, when it comes to measuring H0, the SHOES analysis, which, as I said, uses the Pantheon plus supernovae, finds an H0 of 73 plus or minus 1 kilometer per second per megaparsec. That's shown here in the green, the constraint. And for comparison with Planck, finding H0 and assuming lambda CDM of 67, there is now what we are saying is past the limit of 5 sigma tension. So it certainly, at this point, deserves scrutiny and discussion, and we'll probably be hearing about that today. Pantheon Plus analysis goes beyond lambda CDM. So for example, we look at extensions to lambda CDM, for example, W0 WA, evolving dark energy. And if you just look at the Planck constraints in this parameter space, the gray contour, you'll find that the gray contour could actually go to higher H0, and it could potentially solve the H0 tension. However, if you combine the Planck constraints with the Pantheon Plus constraints, you find that the Pantheon Plus supernovae constrain WA so well in a way that it doesn't allow in the dark blue contour for a high H0 when combined with Planck. So from this, we conclude that actually WA cannot resolve the H0 tension. The Pantheon Plus supernovae put you in a bit of a straitjacket when it comes to measuring the evolution of dark energy or possible deviations from lambda CDM that could, in the late universe, resolve the H0 tension. Looks like I have another couple minutes, so I want to just touch upon this slide here, which discusses the robustness of the supernovae and their role in the distance ladder approach. So there's two papers that have come out as part of the SHOES analysis recently. A two-rung distance ladder led by Darcy Kenworthy, where it throws out the supernovae, and what he finds is that yes, the measurement of H0 is dominated by systematic uncertainties, namely in the characterization of peculiar velocities and also in your selection function, whether or not you're redshift limited or distance limited. So the constraint on H0 is limited, but he does find a relatively high H0 and decent error bars, enough to give us confidence in that it's not the type 1a supernovae that are pushing H0 high. In addition, on the right side, I'm showing a paper by Pete Garnovich, which is a 4-rung distance ladder. So now, why would you do a 4-rung distance ladder? Well, there is some discussion about the role of the host galaxy environments of the type 1a supernovae and how they may contribute to systematic uncertainties in H0. And so by adding an extra intermediary rung, that being transferring the Cepheid calibration to surface brightness fluctuation calibration, you get a different set of supernova host galaxies with a different set of masses, shown here in the plot, and a different set of supernova properties compared to the Cepheid host, so comparing the red to the blue. And what you find is you still get a high H0, despite looking at a completely different set of host galaxies for the second rung of the distance ladder. And so with that, I'll leave you with a plot on the right, which is W0 WA, from our most recent analysis in the blue contour, and then I'm showing forecasts from Rubin and Roman, and it's a bit of a cheeky plot, but it should hopefully excite you that there's definitely exciting possibilities of discovery on the horizon. The Pantheon Plus data set, light curves, cosmological chains, and our entirely reproducible analysis pipeline is actually posted on GitHub. And up next for me is the Dark Energy Survey 5-year final analysis of 1,500 photometrically classified supernovae from a single telescope. And that is something that I'm co-leading with Maria Vincenzi, who's really awesome. And she has essentially solved one of the biggest barriers to that analysis, that being the machine learning photometric classification problem. She's essentially solved that problem. So it's really facilitating an exciting analysis coming up soon. So keep an eye out for that. Thanks very much.
Thank you, Dylan. Do we have any questions in the audience? Anybody online? Yes. Do you mind saying your name?
Hi, Dylan. This is Jose. So I'm curious about the high omega matter value that you're getting, like how this, I mean, I know for Planck is definitely smaller, but then like for other surveys, like how it compares, and also do you know like the origin or do you have ideas on this?
Yeah, it's a little high. I do know that the Dark Energy Survey 3x2 point analysis got even slightly higher, I think. So it doesn't seem too crazy. I know that the value of omega matter does play into some of these early universe models. So I highlighted that because it kind of pulls some of the crazy, early dark energy models in different directions. So it's an important number to keep an eye on. I don't think it's a crazy number, though.
We have time for one more quick question. Yes.
Hi, hi. I'm Luis, and do exoplanets, so I have no idea what cosmology is. The one thing that I kind of know is that there's also the value of H0 from kits, and how does that compare to what you were showing from the kilodegree survey?
I don't know the H0 value from kids. I'd have to look that up. Yeah, apologies.
Okay. I'll ask offline. Thank you.
Thank you. All right, everybody, let's thank Dylan again. Thank you so much. Great.
Yeah.
All right, up next we have Anwar Shazip, who is a 2021 Einstein Fellow. Do we need help? Okay.
Okay.
Good? All right, great. Thank you.
Can people hear me through this mic? Okay, thank you. Thank you, Ariana, for the introduction. As Ariana said, my name is Anwar Shazip, and today I'm going to continue on the theme of Hubble constant measurement from Dylan's talk. So this plot here compiles all the recent major measurements of the Hubble constant until last year. So Dylan already gave you a preview of the Hubble tension, which is primarily between the CMB-based measurement coming from Planck and the measurement based on distance ladder calibrated by different types of stars. So given this tension, it's very important to have different independent methods to measure the Hubble constant, because independent methods will not share the same systematics. So if different independent methods point to this same Hubble tension with high level of confidence, then it would point to some new physics beyond the lambda-CDM cosmology. So today I'm going to talk about this bunch of points here, which are coming from strong lensing time delays. Or we also call it as the time delay cosmography. So in a strong lensing system, if there is a background source that is being lensed by a foreground massive objects, you see these multiple point images appearing, and also sometimes a full Einstein ring. So from the background source, if two photons are emitted at the same time, and they appear at different image positions, they have traveled different cosmological distances when coming around the foreground galaxy, and they have also gone through different depth of the potential well created by the foreground galaxy. So these two factors create a time delay between the arrival times of these two photons. So if we have a transient source as the background source, then by monitoring the light curves of the background or the images, we can measure this time delay. So you can see in this video that it spans over multiple years. There is a noticeable delay between the light curve of image D with the other three light curves from the other three images. So now, from this measured time delay, if we factor out the contribution coming from the gravitational potential, this delta psi term, then what we are left with is only the geometric contribution. That is simply a combination of the three angular diameter distances involved in this lensing system. And we call these particular combination as the time delay distance, which is inversely proportional to the Hubble constant. So that's how we get from the measurement of the time delay to the Hubble constant. But how do we estimate these lensing potential difference term? So to do that, we model the density profile or the mass distribution in the lensing galaxy, and we do that using high-resolution imaging data of a lensing system. So this one is a Hubble Space Telescope image. By lens modeling, I mean that we need to have a model that can predict or reconstruct this imaging data. So in our lens model, we have several components. So one component is a description of how mass is distributed, so the mass surface density profile. A point of note here that we usually take a power law profile radially with an elliptical shape azimuthally. So why the power law profile? So the power law profile has been observed to be consistent with several non-lensing studies, for example, stellar dynamics, X-ray intensity, and although it is simplistic and easy to compute the lensing properties and do the lens modeling, but it is also very capable of fitting our data to the noise level. So next, the next component is a description of the source galaxy light profile before it was lensed. So you can see this is a reconstructed light profile, but it looks roughly like a spiral galaxy. We also need to have a model for the PSF. So now, given these model components, the model then recreates the observed image, and given this predicted image in comparison with the imaging data, we can optimize the likelihood function that constrains the model parameter, and then in turn, it gives us the estimated lensing potential difference, the delta psi term. So this method has been applied to 7 different lens systems so far by the TD-Cosmo collaboration, which is an umbrella collaboration formed out of previously known Holy Cow, Sharp, and Strides collaboration. So out of these 7 systems, 6 were analyzed blindly, so we didn't look at the Hubble constant until we finalized all the analysis. And you can see in this plot here, the individual measurements from each of these systems are shown in these colored distributions, and the combined measurement from these 7 systems are is this black distribution. This plot is showing this measured value in comparison with the other prominent measurements. So for example, the shoes measurement that Dylan was just talking about. So you can see it agrees very well with the shoes measurement at this point, which is in tension with the CMB base value. So until now, this is the past section of my talk. Going into the present, I'm going to talk about the major source of potential systematic in this method. So I'm going to give you a qualitative description of this degeneracy called mass sheet degeneracy, which is very well known for lensing. So if we take a power law mass profile and plot it on a log-log plot of density versus radius, then it looks like this straight line. And as I said, this model is very well capable of fitting our imaging data up to the noise level. Now, there is a transform, it's a mathematical transform called the mass sheet transform. If we apply this transform to this mass profile, the transformed mass profile may look something like this. And the nature of this transformation is such that this new mass profile is also equally capable of fitting our imaging data. However, after the transformation, this is not a power law model anymore. So now this new mass profile will give us a different prediction for the velocity dispersion of the galaxy. It predicts a new unlensed source brightness before the lensing magnification, and it would also change the Hubble constant. So because we are not allowing this type of mass model by describing our mass model only as a power law, although this mass model can be allowed by the data, we are not allowing this to be explored in the modeling. So this can be a potential source of bias in the resultant Hubble constant if the galaxies deviate from the power law assumption of the mass profile. So we do not know if that deviation happens. The current data only tells us that power law assumption is consistent up to 5%, but we want to measure Hubble constant to 1 to 2% precision. So to marginalize over this systematic, we have rebuilt our experiment where we relax this assumption on the power law and constrain the mass sheet degeneracy only using stellar velocity dispersion of the lensing galaxy. So this plot is showing what happens if you do that. So starting from the top, this is the previous measurement that I showed in a previous slide with the 2% measurement, assuming galaxies follow power law. And if you do not have that assumption, then the uncertainty naturally increases to 9% because now the uncertainty is dominated by the uncertainty of the stellar velocity dispersion measurement. So to gain some precision back from here, we can add a prior on the mass profile shape using an external sample of non-time delay lenses. So we have used a sample of SLAC's survey. These are non-time delay lenses, but because they are larger in size, we can use their stellar velocity dispersion to have an informative prior on the mass profile for the time delay lenses. So once we do that, we gain in precision. So now the precision is at 5%. But interestingly, the value shifts towards the Planck value. One important assumption here is that the SLAC's galaxies and the time delay galaxies are from the same population of galaxies, which may not be true given they are at different redshift. One is at a mean redshift of 0.2 and the other is at mean redshift of 0.6, but we do not know that yet if they are really different or not. Also keep in mind that all of these values are consistent within 1 sigma. So there is no internal inconsistency between these different uncertainties. All right, so now going into the future, we want to measure Hubble constant just using our method independently to 1.5% precision. And without any mass profile assumption. So the first way to do that is to break the mass sheet degeneracy with a specially resolved velocity dispersion, which is more effective in breaking this degeneracy than the previously used integrated velocity dispersion from a single slit spectra. So if we have 40 time delay lenses with JWST quality IFU velocity dispersion, then it would give us a 1.5% precision. So now we have a cycle 1 JWST program approved to obtain near-spec IFU spectra for one TD Cosmos system, so we all are excitedly waiting for that data. The second way to break the mass sheet degeneracy, if we can know the unlensed source brightness of the background, which we can do for lensed type 1a supernova. So this plot is showing the improvement in the Hubble constant precision over time as we discover more such systems from future surveys like the Rubin Observatory LSST and Roman. So after about 10 years of LSST, the projected number for these discoveries is 144. That would give us a 1% precision in the Hubble constant. So the third way to gain precision back is to have a large sample of external lenses, which are non-time delay lenses. And we need about 200 of them to help us get to below 1.5% precision in the Hubble constant. So right now, I am working with a graduate student colleague, Chini Tan at UChicago, to analyze a sample of about 180 archival lens systems. And this is assembled from many different surveys. So the tricky thing here is to account for the non-uniform selection function because these samples are coming from different surveys, and we are actively working on that right now. But in the future, LSST and Roman will discover even larger samples of these type of systems, which will be more helpful in getting to below 1.5% precision in the Hubble constant. So with that, I'm concluding my talk. I'll leave the summary slide up here, and I'm happy to take questions. Thank you.
Do we have any questions from the audience? Yes, I'm going to go over here first, and I'll come back. This won't make noise when it goes off. Okay, great. Good question.
Can you go back to your slide where you showed the 7 different systems with the sort of error profiles? Yeah. How much does the number jump around if you just don't use that like top purple guy? Because I feel like there's a huge spread here, and how sensitive is to the selection, like sub-selection of systems that you use?
So this is very robust. So even if we remove like a random number or system, then it doesn't move out of the statistical agreement. And so it looks like it has a long tail towards a large value, but it has large uncertainty that also goes towards 70. So none of this system is inconsistent with each other given the individual uncertainties statistically.
Okay. It's going to be really interesting when you said like there'll be a bunch more of these systems with JWST data.
Right. So, yeah.
Mike, right? Yeah.
Yeah, it was really interesting to see how the constraints changed when you added the flexibility in the prior and on the profile. First, what can you remind me what exactly defined the prior that you used, the prior choice that you used? And secondly, are deviations in this choice of prior going to affect your constraints significantly, or yeah, like how does your prior choice affect the constraints that you get?
So, so basically what we're adding as an information in the prior is how much deviation there is from the parallel, right? So that changes the Hubble constant. So now given the lens model of the SLEX galaxies and their velocity dispersion, we have prior on that deviation, and then we apply it to the lens galaxy, to the TD Cosmo lens galaxies. So, but internally, it's, you know, like we do like the full hierarchical Bayesian framework, et cetera, et cetera. But I mean, is this sufficient for your question?
Yeah, that's okay. Fine. I was just wondering if there's any flexibility in the prior that could change the results, or if you're doing this based on actual observations and data.
No, so basically the prior is fully data dependent. So there is like, this is right at this point fully conservative. So we are not like, we didn't have any, you know, knob to turn anymore. Yeah.
Awesome, thanks.
We have a question online from Dylan. Dylan, if you want to unmute yourself.
Sure, yeah. Is there any kinematics data on any of the TD Cosmo lenses?
Yes. So we have integrated velocity dispersion for each of these systems. So they're coming from a single slit spectra. So yeah, we do have that for all the systems. So now, if you're asking about the special result velocity dispersion, so we have been working on that, but ground-based instruments have been challenging so far to get special result velocity dispersion for these systems to the requirements for our analysis. But yeah, we are looking forward to JWST and other new instruments and
okay.
systems.
Yeah, great. Thanks.
All right, let's thank Anwar again. All right, please welcome to new 2020 Einstein Fellow. I guess we should. Okay.
Oh, great. Okay. Yeah. Hi, everyone. So I'm Xingyu, and I'm going to continue this along the line of H0 measurement, but now using gravitational wave observation. And we are using this method called standard Sirens method. Among different approaches of standard Sirens, especially the one that's using electromagnetic counterpart, or you can call it the bright standard Sirens, turned out to be probably the most promising one. And here's how it works. Let's say we obtain, we receive a gravitational signal in LIGO Virgo, and you also happen to capture its electromagnetic counterpart. Then this counterpart identification allows us to localize the source very well on the sky, and that allows us to associate the gravitational wave source to its host galaxies. Then, by measuring the redshift of the host galaxies, we can determine the redshift of the gravitational wave source. On the other hand, the gravitational signal itself directly carries the information of the luminosity distance to the source. It goes inversely as the amplitude of the gravitational wave signal. So we can combine both of these informations and then constrain a set of cosmological that's written in the bottom, including omega matter, omega lambda, H0. And this method has already been realized by the event, the binary neutron star merger event, and its kilonova counterpart. The blue contour you see here, that is our H0 posterior obtained from this event, and the uncertainty is big. However, the projections for the future is that we are going to get more gravitational wave and electromagnetic wave joint detections. So going to the right is going to the future. What you see in the upper panel is the projected number of joint detection. The green vague band there is trying to capture some major uncertainty for this estimate. You might see some different number in the community, but the bottom line is that with a few tens of events like this, we will be able to constrain the Hubble constant to percent levels, which is a precision that can possibly help us to say something about this H0 tension. But let me remind you, the major role for gravitational wave observation in cosmology is not to provide the most precise H0 measurement. Instead, we want to provide a measurement that's independent and hopefully with a measurement that's with a systematic that's to the minimum level. So systematics turns out to be the very important topic for the standard siren measurement. That's what I'm going to discuss in the following. So for a while at the beginning, the community has been only talking about this source of systematic, the instrumental calibration. I'll come back to this very soon. But once you have the first one, the rest follows, just like LEGO events. So yeah, that's a lot of trouble, but let me try to organize these troubles a little bit by which exact parameter it is they are affecting. Either they affect the distance, redshift, or the entire population. And I won't have time to cover all of them, but let me go through some of them. Let's start with, for example, the gravitational wave waveform systematic. And you probably already seen these green waveform from different talks. That is a typical gravitational waveform coming from a binary mergers. There is the in spiral part, there's a merger, and the ring down part. And the way we try to infer the parameters of the binaries from our signal is by first constructing the gravitational waveform template bank. And then we try to match the signal to the templates inside this bank, find out the best fit template, then we recover the parameters. But you can imagine if your bank is not perfect, then the recover parameters would be not perfect. And that introduced some systematic, especially some problem for binary black hole mergers. However, if we are only interested in measuring the distance from binary neutron star mergers, then it turns out most of the information comes from the in spiral part of the signal, which we do have a good understanding of the physics of, and that's why this is probably not a big problem for us for standard siren measurement. Another source of uncertainty comes from the instrument, the instrumental calibration uncertainty, which comes from the fact that we are not able to perfectly convert the voltage signal received in our detectors to the data. So the magnitude or the phase we measured from the signal is not perfect. There might be some bias. And this is one of the long thought to be the dominant systematic. And recently, a work led by a grad student at MIT, Eva Hong, we tried to work with the LIGO calibration team, and we asked how much H0 bias you're going to receive if you have this kind of miscalibrations. And if you look at the green dot there, that is showing how much bias it is obviously deviate from our simulated value. That is a dotted line there as you accumulate more and more events. However, it is actually, this will be a more realistic case because this miscalibration moment in our interferometer don't really overlap with our event that often. So maybe it is closer to 10% of the time while our event overlap with some terrible moment in our interferometer, basically. And that's why we actually don't expect this kind of systematics going to dominate in the future. So far, I've been talking about all the systematic coming from the gravitational wave side. What about the electromagnetic wave side? Well, first of all, you got to get the correct counterpart. And for some of the gravitational wave sources, if they have weak or undetermined counterpart emissions, then that can be a trouble. a clamped counterpart associated with a binary black hole merger. This one is a very good example. After these clamps, you can, not surprisingly, there are various H0 measurements being produced, including myself, but actually we have to be more careful. We do need more statistics to establish the counterpart association probability. There's nice work led by Antonella. I believe she will talk about it a bit more. Otherwise, you might not want to include some of these events into the analysis. Redshift information is not the only information we can possibly obtain from the EM side. Once you have the observation, you can try to analyze your electromagnetic emissions and then try to constrain some more binary parameters. One of the important parameters you can try to constrain is the binary viewing angle because it has to do with how well we can measure the distance. So there are various groups trying to constrain the binary viewing angle better and then improve the distance measurement, therefore the H0 measurement from the GW17-OS17 event. But one question you could immediately raise is that, well, what if this inferred viewing angle is biased? You can underestimate, overestimate this viewing angle, and yes, that's gonna produce a big problem for you. So what you see here, everything shows that with a few degrees of bias in the viewing angle you infer, you can easily push a Planck H0 value all the way up to the Schuss value, the supernova value, which is the last things you want. So I would say you don't need to use this extra information, extra constraint, but if you do want to use it, you have to be more careful. Okay, so now let's talk about selection effect. Selection effect from the gravitational wave side is actually well under control. That's because we have a very good understanding of our LIGO-Virgo sensitivity and also very good understanding of how bright a gravitational luminosity is coming from binary mergers. That is not the case for electromagnetic wave side. For electromagnetic signal coming from binary mergers, we don't have a solid or widely approved models for example, the kilonova emission yet. And this not enough understanding of the counterpart observability can give you unknown selection effect. Let me just give you a very simple example here. Let's say you can only observe the electromagnetic counterpart within certain opening angle. This is a very simplified example. And depending on how wide this opening angle is, let's say you don't really know about this selection effect. Again, you can easily push a H0 value starting from the Planck's all the way to the Schuss value. And this kind of systematic, I would say, is different from other systematic I just talked about, because other systematic, you can probably do something about it, either throw away information, throw away events. It's not good, but unless it kind of solves the problem. While this one is kind of intrinsic, it is there in your population. Once you infer with more than one event, it is there. And that's why it worries me more. I'm worried that this kind of systematic is going to dominate our future systematic for the bright standard siren measurement. I look a little bit further into this with more realistic model, for example, taking some kilonova models and applying some real telescope like ZTF, one of the possibly the dominate discovery machine for kilonova. I can easily show example that give us a few percent level of bias in H0, or I can find another example that give me almost no bias or even negative or bias into the other direction. So it seems that there is no universal solution to this systematic yet, and that is something I'm still looking into. Thank you. So I'll stop here with list of our trouble. Thank you for listening to our concerns. We are still working on it, and my goal is to make sure standard siren method will work properly when the time comes. This is also my last year of the fellowship. I really just want to thank everybody behind this program. The freedom, the support, I guess, just tremendous. Thank you.
Thank you. Any questions from the audience? Mike?
Thanks for the talk, Xinyu. Does the GRB viewing angle play into the systematics as well? So, I mean, you're talking about how different understandings of our viewing of the kilonova can affect H0 measurements, but when you incorporate information from us seeing a GRB or us not seeing a GRB, can that help to constrain this degeneracy a little better?
It certainly would help if you can, first, if you understand the GRV emission model very well, which is better than what our understanding for the kilonova one. So it certainly helps. We will still need to be careful about the systematic because we are really requiring few degrees accuracy. And that's tough.
Thanks for the nice talk. So a related question, what is exactly about the kilonova that produces that bias? Is this something related to the inclination angle or something else?
So inclination angle is one factor. You can imagine different mass combination will give you different light curve, but if you don't know exactly which dependency it is, then it will give you the same type of bias. Mass is slightly better than inclination angle though, because gravitational waves are able to measure the mass to a certain precision, while inclination angle is just terrible. So that's why I'm more pessimistic about the inclination angle induced systematic. Yeah.
And we have one question online from Dylan. Dylan, you can unmute yourself.
Hi, Xinyu. Really nice talk. So in that last slide for the dominant systematic, the viewing angle selection, it looks like fully degenerate. Is there a realistic estimate for like how dominant this is, or you see it being in the future? Like, is this
the systematic one?
How devastating is this? Is it devastating?
I don't know. I'm not that pessimistic so far. So there are two-folded problems. So first of all, you don't understand the kilonova model. So let's talk about that one. That one, you can imagine that once we have more kilonova observation, then this parameter space will also improve. So I'm hoping that at least we can reduce these number of models by a bit just from future kilonova observation. That is our first problem. But second problem is that we also need to have the observability map for different telescopes. That is more a community problem, less a scientific problem. And that is also something I am not so sure how well we can deal with it. But as I said, it's not a scientific problem. It's more a community problem. I don't know. I cannot give. Yeah.
Thank you. Thank you.
Thanks, and you again. Thanks. You.
Great. It's a difficult one. Efkiaka. Yeah, that's perfect. Okay.
All right, please join me in welcoming Jose Ezquiaga, 2019 Einstein Fellow.
Thank you, Ariana. Thank you, everybody. So I guess, H0 is great, but I'm going to argue that, no, especially for the future, like gravitational waves are going to open like a really interesting and promising window to explore the early universe. So I had this slide last year, but I'm lucky enough to be here for the fourth time. So thank you again for holding this program. It's really like fantastic to be here. So we saw from Mike's talk something similar to this plot, but I thought it was good to emphasize it again, that gravitational waves are intrinsically cosmological sources. So when you think about where these mergers from binary black holes happen, they really do happen billions of years ago. And when we think about our horizons, how far we can detect these sources, we are very rapidly gonna cover all the space. So we are essentially now, we had 3 observing runs. We can see a few billion years away. But then we have already planned improvements with our current detectors that will allow us to go close to Redshift 1 and beyond. And then with the next generation of detectors, which is what really excites me, we're going to essentially observe all the binary black holes that merge throughout the history of the universe. And this is really great when you think also about studying cosmology, because we are here, you can measure the expansion and get H0, but when you look back in time, there are different components that are relevant. You can study dark energy, as we heard from Dylan, but also you can learn about dark matter and other components. So we also heard the basics from Xinyu, but just to emphasize again, when we have 2 compact objects that merge, they perturb the space-time, and these gravitational waves travel across the universe. And during this trip, they get 2 main effects. Their amplitude decreases just because it's a spherical wave, so it's inversely proportional to the distance, and also because the universe is expanding, they get redshifted. So in our detectors, we are only sensitive to the luminosity distance through the amplitude, and also the redshifted or detector frame masses, just because we get the masses from the frequency evolution of the signal, and the signal has been redshifted. So if you focus on the luminosity distance and you get external information of the redshift, you can do bright siren cosmology, as Xinyu was saying. If you use galaxy catalogs, you can do dark siren cosmology. But what I want to focus in this talk is what is the cosmology that you can do only with gravitational wave information, without using any additional input. And this amounts to focus not only on the luminosity distance, but also on the masses of the sources. So this method we like to call the spectral siren method, and that's because it accounts to look at the spectrum of the masses. So in some way, it's reminiscent to how you look at the spectrum of galaxies to identify the redshift. So anyway, so in our detectors, we are counting how many events we get of different masses at different distances. And then you can essentially just make histograms. I get 10 events that have 10 solar masses. I get 5 events that have 50 solar masses, etc., etc. So you can build your population, your counting events as a function of distance. Okay. It's not in my presentation. Anyway, so when you are thinking about detector frame masses, just because they have been redshifted, the farther you go away in distance, the heavier the masses are. So you're moving to lower frequencies to higher masses. So your spectrum, as you move back in time, you are shifting it. You are shifting all the masses. And then what you can do is you can look from your model for your population nearby and see how much it has been shifted. I don't know what it is. And this will allow you to measure cosmology. Okay, well, anyway, so for example, if I were to change H0 to a higher value, then what you are doing is that you will shift all your masses you will shift them farther away. And for example, if you lower omega matter, you can do it in the other way. So just to stress, the strength of this method is that you are doing astrophysics and cosmology at the same time, so you can use all the sources from our gravitational wave catalogs, not only binary neutron stars with electromagnetic counterparts. So this is something that you can do with every catalog that we have now, and in the future you can apply this method. And you can think of studying it for binary neutron stars, binary black holes, or even like heavier black holes. But at the end, what you want to do is use all the information that you get. So I will be focusing in the rest, results from this recent paper, but there's been a lot of work studying like different aspects of these ideas. So of course, I'm sure you're all thinking that, okay, this is great, but we don't really know what is the intrinsic population of these sources. We also expect like environmental effects to affect the formation of binary black holes. Are there degeneracies between astrophysics and knowns and cosmology? And I think here, again, the point to stress is that cosmology is something which is common to all the sources. So it's a global effect that just in your detector frame masses shifts all of them. While astrophysics, what it's going to do is that it's going to change the shape. So at the end, if you want to frame this from a data analysis perspective, your astrophysics changes the shapes, and then like cosmology just shifts. So you are looking for shift plus plus changes in the shape. And quoting myself from the abstract of our paper, I think the key is that you can break these degeneracies by using the full mass distribution, because you don't expect all the masses to be changing at the same rate that cosmology does. So in order to have a true degeneracy, you will have to have kind of like a astrophysical conspiracy. And you can also see this, for example, in this plot, when you think about your inference in the Hubble expansion rate as a function of redshift. So, for example, if you change H0, you are just changing up and down your Hubble parameter. If you change omega matter, this affects at higher redshift. And you could think like, okay, what if I'm having like some evolution of my mass distribution that I'm not aware of, and then I'm inferring wrongly the redshifts? Then what you would see is that maybe at low redshift there could be some confusion, but as you go to high redshift, the rate at which the masses change doesn't match what you expect from cosmology. So we are now, as I said at the beginning, we had 3 observing runs, about 100 events, most of them below redshift of 0.6. With current detectors, second generation, we will move in 2025 plus to thousands of events, with some of them beyond redshift 1. And then the exciting part for me is, which is a bit far in the future, it's more than a decade, but still very exciting, when we will have hundreds of thousands of events per year, many of them beyond redshift 1. So as a toy example, I will consider a population of binary black holes in which I'm going to allow for changes in the minimum mass and in the maximum mass. And I'm going to infer cosmology and astrophysics with those. So if we take a scenario of next generation detectors, just one month of data, this accounts for 10,000 events. So just with 1 month of data, let's analyze our population without including evolution in our model. So here, these are the posteriors for H0 and omega matter, and the blue posteriors corresponds to a injected population that doesn't have any evolution. So then what you see is that you recover the I was injecting standard Planck cosmology, so you recover that. If you change your minimum and your maximum mass, and you are not including that in your model, this is your red contour, and then you are really biasing definitely your results. If you change only the maximum mass, just because with next generation detectors, there will be many more low mass black holes. If you are only changing the maximum mass, you are shifting a bit your values, but the true feature that is anchoring the cosmology is the peak at low masses, so your cosmology is not that biased. But of course, what you want to do is to include in the analysis both astrophysics and cosmology, and when you do that, you get a picture with this consistent. So this means that you measure both H0 and omega matter, and also your parameters doing the evolution. Thank you. So this is very exciting because what this means is that we have the possibility of doing really precision cosmology, meaning sub-percent precision in the Hubble expansion rate beyond redshift of 1. And this is very nice because when you, for example, compare to other probes from galaxies and Lyman alpha and such, it becomes very tricky and difficult to constrain at high redshift. But since we will have so many events, redshift of 1, 2, and beyond, this is an exciting avenue to explore the expansion rate at high redshift. You can also do the same, of course, with current detectors, and what you would get is better than 10% with 1 year of data at around redshift of 0.7, which is also very exciting. So this is all I wanted to say. You can do cosmology with the full mass distribution of compact binaries. This is very exciting for the future especially, so thank you for your attention.
Okay. Any questions?
I think there is a question from...
Speaking of maximum mass, is it relevant or interesting, the more distant future with nanograv and merging of supermassive black holes?
Right. So all this talk was thinking of ground-based detectors, which are sensitive to like solar mass, like tens of or 100 at most solar masses. With supermassive black hole, I think this is exciting more than for nanograph for LISA. And for those, I think the exciting thing is that these are sources which will be very long in band, so they will be like maybe a month in the LISA band. So this means that they can be localized much better. So then, like, you can aim to look for galaxies which are within the error in the localization. I don't think this method will apply to that because this really also benefits from the enormous number of like detections. So it's a population analysis of the more the better. But for LISA, I think we will get like kind of like hundreds of events. So it's not that, I think, that's relevant, but it's very exciting for LISA just to look at like the supermassive black holes and the small localization that they will have.
All right, let's thank Jose again.
Thank you.
All right, please welcome 2021 Einstein Fellow, Antonella Palmeser.
Okay, can you all hear me? Okay. Yeah. All right. Hi, everyone. So today I want to tell you about, in particular, two types of multi-messenger standard siren measurements that I find exciting also in light of the upcoming LIGO Virgo and Kagra observing runs. So first, I'll be telling you about the most standard siren method, which we already heard about from Sinu, which is that from binary neutron star mergers. And in particular, I'll give a brief update about a measurement from GW170817, which was the first binary neutron star merger to be detected in gravitational waves, and also the first and so far the last one to have an electromagnetic counterpart. Then I'll tell you about standard siren measurements with binary black holes that merge in AGN disks. And then I'll briefly advertise some observations that I'm doing with the dark energy camera, the DESERT program, which are also helping me in preparation for the upcoming observing campaigns with GCOM. So I'm sure you're all bored by now to hear about the Hubble tension. So I'll just remind you that if we're interested in understanding this discrepancy, and we're looking for an independent measurement, independent from the cosmic microwave background probe and from the supernova type 1a measurement, then ideally, if we're looking at a probe that is from the late time universe, like the gravitational waves that I'll be telling you about, then ideally we want it to be independent of the same sets of systematics that might bias the supernova type 1a measurement. So ideally independent of the cosmic distance ladder that we heard about from Dylan. So gravitational waves do offer that possibility because we can get the luminosity distance directly from the gravitational wave data. And then if we're able to get a redshift somehow for that same source, we can populate the Hubble diagram and measure the distance redshift relation. So unlike what Jose just talked about, I will only talk about standard siren measurements that do make use of external data of galaxies measurements of redshifts. So in this case, we mostly talk about bright standard sirens when we have a counterpart and a unique host galaxy, and dark standard sirens when we don't have a counterpart. And so we're taking into account all of the potential host galaxies within the localization volume. And the latter one is what I talked about last year at the Symposium. But this year also introduced something that is kind of in between these two methods, which is using AGN, so just a fraction of the galaxies in the localization volume. So let me start with the former case with the bright standard sirens. So if we're interested in making this measurement, then we have to look for the electromagnetic counterpart. So in the case of binary neutron star mergers, what we do expect in terms of counterparts is observations at different wavelengths. So when the two neutron stars collide, we expect the formation of a relativistic jet that you see here in the video in magenta that we expect to be able to observe in gamma rays, at least if we are on axis with the binary. We also expect to see a thermal transient that is called the kilonova. The here is shown by the violet and white ejecta that we expect to detect in the UV, to the optical, to the infrared wavelengths. And then at last, we expect to see an afterglow that is coming from the interaction between the relativistic jets or even the kilonova ejecta with the interstellar medium. And this is something that we can possibly observe all the way from the X-rays to the optical to the radio wavelengths. For the case of GW170817, it was the kilonova detection that enabled us to actually pinpoint the host galaxy, so precisely find the location of the counterpart. But it is the data from the afterglow that we now have out 2 years after the detection of 170817. So what we're doing in this analysis, including all of the data that we have for the afterglow from the X-rays to the optical to the radio wavelengths, to try and get a better measurement of the viewing angle, as we heard about from Sinu earlier, to try and break this degeneracy that exists from the gravitational wave observations between the luminosity distance and the inclination angle, or similarly, as you see here, between the luminosity distance and the viewing angle from the gravitational wave data. Here you see the posterior in blue. Now, from our modeling of the afterglow, we can get this posterior here that you see in red that clearly helps us to break this degeneracy. So this way we can get a better estimation of the luminosity distance and in turn a better estimation of the Hubble constant. And so you see our updated constraint here in red, which you can compare to the case in which we don't use that extra information from the afterglow. Here in blue, this is posterior distribution on H0. And so we're roughly getting a factor of 2 improvement on the uncertainty on H0 in this case, reaching about a 7% precision measurement But this is still consistent both with the early and late time universe measurements. They're given here by these vertical bands. So we're not able to say anything about the tension at this point, but we will in the future. Now let me switch to the second case. So standard sirens with binary black holes in AGN disks. So we heard from Maya earlier this week about the origin of the binary black holes that are being detected by LIGO, Virgo, and Cagra being still unknown. So one of the interesting, at least in my opinion, formation channels for these binary black holes, and especially the most massive ones, is the fact that they could merge in AGN disks. So this is a great environment for repeated mergers, for example, if they happen to be in one of those migration traps in the disk. But it's also interesting for an observer like myself because there is gas around the binary in this case, so there could be also an electromagnetic counterpart that comes together with the merger thanks to shocks with the gas or accretion onto the remnant black hole. So this is particularly interesting if we also think about the AGN flare that was found in coincidence with 1905-21. And here you see the light curves from the Zwicky transient facility in GNR band, and you see the flare right after the detection of the gravitational wave event. Now, what we actually find for this specific event is that because this was one of the events with the largest localizations out of all of the gravitational wave events that we have so far, it also encompassed a large number of unobscured AGNs, and AGNs do vary all the time. So we find that there was actually about a 70% probability of chance coincidence of finding a flare within this very large localization volume at the time of the gravitational wave event. But we thought it was still interesting to ask the question, how many of these flares or how many of these events do we need to follow up to establish a confident association between the gravitational wave events and the AGN flares? So we came up with this Bayesian formalism, basically trying to constrain this parameter lambda, which is the fraction of binary black holes that give rise to AGN flares, and just looking for basically one signal AGN, the AGN where the binary black hole is actually happening, on top of some background AGNs that may be varying at the same time. So here is the number of follow-up that are needed in order to establish this association, and that is a function, obviously, of the true value of this parameter lambda. So if you have a smaller fraction of binary black holes that are happening in the AGNs and the rest is coming from isolated binaries, then you'll need more to accumulate more follow-ups to establish this association. And when we look at simulations for the upcoming observing round 04, we get this orange curve, which means that as long as this fraction is at least 10%, we might be able to get the association with something like 10 follow-up of binary black holes. So then we can extend this formalism to not only constrain lambda, but also constrain cosmological parameters at the same time as a standard siren methodology. And obviously here we're trying to extend beyond H0 measurements, also here omega matter, but also dark energy equation of state, since we're going beyond what we have been talking about for binary neutral star mergers that will only go out to a few hundred megaparsecs for the coming years. And then we can also think about extending this to AGN locations. So instead of looking at the flares, we might just look at all of the AGNs in the localization volume. And so this is still better compared to the dark standard siren method because the AGNs are only a small fraction of all of the galaxies in the volume. So this is another method that we are currently exploring. So some forecasts for this method, at least for H0 measurements. So what we expect from the catalog level case without the flares is that we might reach something like between a 4 to 8% precision on H0 between, if we're looking between 10 and 80% of the binary black holes being of AGN origins. And some papers show that this number should be between 20 and 80% potentially. In the case of the flares, with a 1-year run, we are here constraining to a smaller range of lambda values because we expect to see the flares, at least in this case, I'm interested in looking at flares in optical bands. We only expect to see those if they happen in unobscured AGNs. So we only look at a smaller fraction. And here for 1-year run, we expect to be around a 5% precision on H0. Again, assuming that some significant fraction of these events actually happen in AGNs. So the last 2 minutes, I'd like to briefly advertise this DESERT program. So the DESERT program is something that we're carrying out with Lifang Wang using the dark energy camera, or DCAM, which is still a great instrument for gravitational wave follow-up. One of the reasons being that it has a quite large field of view, about 3 square degrees, and it's mounted on a 4-meter telescopes that let us go quite deep to look for those faint kilonovae. So even though this was built for the dark energy survey and dark energy survey is over, we're still using DCAM as a community instrument to go and follow up these events. And we're doing this as part of a big network of follow-up facilities, including next year JWST. So in the meantime, while we wait for gravitational wave sources, we're carrying out several actually time domain programs with DCAM. The one I'm working on in particular is called DESERT, the DCAM Survey of Intermediate Redshift Transients, and we're looking at GRZ observations, trying to look at the same place where DESI, which is a multi-object spectrograph, which is currently ongoing, is looking at, so that we can get at the same time redshifts of host galaxies, of the transients that we observe, and very often we also get the actual spectra of the transients. We can also repoint a few fibers, the spare fibers, to actually observe as target of opportunity our transients. So we're looking at about 100 square degrees every 3 to 4 nights. We're finally, as of a few weeks ago, we're finally running our difference imaging pipeline on NERSC GPUs, which means in about 50 seconds, we're going from images to alerts, and this is going to be very important in the gravitational wave follow-up next year. We're also sending out public alerts. You can see more details at the link here, and our DCAM data is actually public immediately. So I encourage everyone here who's interested also in whatever time delay measurements or anything else to go and use it, or come speak to me if you're interested. So there will be some data release also soon with the DESI data release. These are some example light curves that we're currently modeling using a variational autoencoder, and we'll also release with the DESI observations. So to conclude, I'm really looking forward to the next round of follow-ups and hoping to find at least 2 counterparts in 04. Thank you.
Any questions?
Very nice. So I think it's really cool that we still detect like 17 and this give us some information. So when is the limit? Like, and what does it tell us for the future? Like when we like do forecast, like do we have to do a forecast for like a prompt counterpart, but then another like 5 years later? Or yeah, I don't know. If you have some thoughts of that.
Yeah, so I think this was a special case, right? It was very nearby, so that's why we've been able to see things out to 4 years beyond. Now we're hitting the limit where there was a nexus in the afterglow that is probably the kilonova afterglow, so something that could be very interesting. But that's because it's very nearby. It's kind of off axis, so we're still seeing the afterglow, but it was still on axis enough that we could see the afterglow. So it was a special combination of things that might not happen in the future. So that's my thinking, is that we'll not go very often 4 years beyond a detection.
Any other questions on the chat? All right, thank you. And our last talk for this session is online. I see Hailey has joined us.
Yes, I'm here. Can I share my screen?
I think so. Just hang on one second. Okay. Up next is Hailey Mcpherson, oh God, is that a 2022, Hailey?
Yeah,
Hi.
that's right.
Okay. Welcome, Hailey. Please take it away. Oh, I'll interrupt when you have about 2 minutes, all right?
Sure, no worries. All right, let me just try and get this screen sharing going. All right, is that okay? Can everyone see me?
Yes.
And hear me and screens? Great, okay. Awesome. So hi, everyone. My name's Hailey Mcpherson. I'm an incoming Einstein Fellow at the University of Chicago. I'll be starting this November. Right now, I'm currently still a Herschel Smith Fellow at the Centre for Theoretical Cosmology in the University of Cambridge in the UK. And that's where I am right now, and that's why I can't be there to join you all in person. And today, I really just want to give a kind of very broad background and overview to my area of research, which will form the basis for my Einstein Fellowship program, which is trying to constrain nonlinear general relativistic effects using cosmological simulations which use numerical relativity. So our modern cosmology is based on Einstein's theory of general relativity, and this theory tells us that gravitational interactions are described by the geometry of space-time, and specifically that the evolution of the universe is governed by Einstein's field equations. The right-hand side here, in the stress-energy tensor T mu nu, represents the matter content of the universe, and the left-hand side is the space-time geometry represented by the Einstein tensor G mu nu, which tells us about the space-time geometry. And so these equations really embody the intimate relationship between matter and space-time in the evolution of the universe. Now, this system of equations are notoriously difficult to solve, especially for complex systems like the entire universe. So most of the time, across all areas of physics and mathematics, we often make some simplifying assumptions, such as exact symmetries, to make them more manageable analytically. And cosmology is no different. And in cosmology, we typically impose symmetries of exact homogeneity and isotropy. And this means that our space-time and our matter field are the same no matter where we're located in the universe, in the case of homogeneity, or in which direction we're looking, in the case of isotropy. And under these assumptions, we arrive at the Freeman-Lemaitre-Robinson-Walker, or FLRW class of models. And within these models, the field equations are simplified drastically to become the set of Freeman equations shown here on the right-hand side. And within these models, the evolution of the whole universe is described by one function of time, known as the scale factor A. This function describes length scales in our FLRW universe, and so its first time derivative, given in this top equation here, is the change of length scales in time, or the expansion of the universe. And this expansion is directly sourced by the matter content of the universe in rho, the cosmological constant lambda, representing dark energy, as well as the spatial curvature constant k, which describes the scalar curvature of three-dimensional spatial sections in our FLRW universe, and takes one of three values depending on whether those sections are closed or open or flat. Now, the second time derivative of our scale factor tells us about the acceleration of length scales within our FLRW universe, and this depends and is sourced by the matter content, which counteracts this acceleration, and the cosmological constant, which enhances it. And this assumption gives us a very simple set of equations, and these really form the basis of modern cosmology today. Now, very roughly speaking, we can fit these equations to our observations of the expansion of the universe, and we can thus infer how much each of these terms on the right-hand side contribute to that expansion to determine the energy content of the universe. And as I'm sure you're all aware, the current best fit model breakdown of the energy density of the universe looks something like this. So this is within the lambda CDM model. We know that we have about 70% of the energy density of the universe made up by dark energy in our cosmological constant term lambda, and the rest of it is in our matter term rho. And so from this, we can infer that our best fit lambda CDM also has a flat geometry, or a k=0 term, because it doesn't appear in this pie chart. But of course, we know that the universe is not perfectly homogeneous or isotropic, and we know this because we're here to talk about it. We see planets and stars and galaxies, clusters of galaxies, and the large-scale structure of the universe, which is shown here in this 2-micron all-sky survey, where each point is showing an observation of an individual galaxy. So within cosmology, when we really talk about the universe being homogeneous and isotropic, strictly we mean that the distribution of galaxies becomes statistically homogeneous and isotropic above a certain length scale. And this scale varies depending on what kind of measure you use, but is typically around 100 to 300 megaparsec. So an additional assumption that we must then make is that at this scale of statistical homogeneity and isotropy, the geometry of our universe is well described by the FLRW class of models on average. So within the context of fully nonlinear general relativity, this is not necessarily the case, and a statistically homogeneous and isotropic distribution of galaxies is not sufficient to guarantee a space-time geometry which is FLRW. So this is an assumption which underlies standard cosmology, which remains to be thoroughly tested. But of course, this assumption is extremely useful because, as we saw earlier, it simplifies the field equation significantly such that we can still do cosmology and learn something about the dynamics of the universe. Now, the way this assumption actually enters our calculations depends on the regime that we're interested in. If we're only interested in studying the really large-scale dynamics of the universe, we usually assume that we can neglect all of the small-scale, nonlinear physics going on and really isolate these long wavelength modes on large scales. And in this case, we would typically use perturbation theory and thus assume that we can describe this regime using an FLRW background with small perturbations on top. And then Einstein's equations are typically easy enough to solve by hand. However, if we're interested in studying the nonlinear small-scale dynamics of the universe, then we can't use perturbation theory anymore. And this is where simulations come in, which help us study regimes that we can't access analytically. In cosmology, our simulations are typically done by assuming an FLRW expanding spacetime with a cosmic web which forms purely under the action of Newtonian gravity and separate to that expanding spacetime. However, of course, we know that Newtonian gravity doesn't give us the full picture in all cases. And in fact, there are some phenomena which exist in general relativity that are purely absent in Newtonian gravity. And it's therefore really important to consider what differences might arise in our cosmological modeling. And this is where a lot of work has gone into including relativistic corrections in order to try and capture some of these missing effects. And usually these are included as correction terms to Newtonian dynamics or considering beyond linear perturbation theory in general relativity. Others have also looked at some of these effects using exact models within general relativity, such as black hole lattice models, exact solutions like Lemaitre-Toulmin-Bondi, and Zekeresh and Swiss cheese models, for example. So these are all still approximations for our universe, and in particular in some of these exact models, the really simplifying symmetries can sometimes make it difficult to draw accurate and realistic conclusions about our own universe. And so most, if not all, of these corrections generally rely on the definition of some sort of background spacetime. And this is because if we're ever talking about a perturbation, it must be defined on top of something. And it's no secret that all these methods are approximations for what's really going on. The universe doesn't have a background or even necessarily a clear separation between large and small scales. And the use of the FLRW model is an assumption on the average dynamics of the universe. In reality, the universe doesn't know its average, and therefore it doesn't know that it should expand like the FLRW model on average, and it only behaves according to the best of our knowledge, what general relativity tells it to do locally according to the field equations. So these assumptions have been the basis of building cosmology today, and they do a very good job. However, they are still assumptions, and therefore they need to be tested. And the only way that we can really test any assumption is to remove it. So as I said before, these approximations are generally employed because they simplify our equations a lot, and solving the field equations for a complicated matter distribution was just too hard. But our numerical methods have come a really long way. And we now, and for the past few decades or so, have a numerical method by which to remove almost all of these simplifying assumptions about gravity and geometry in our cosmological modeling. And I'm talking about numerical relativity, which is a numerical method that allows us to solve Einstein's equations directly without making any assumptions of symmetry on our underlying spacetime. Now, this method is extremely widely used for about 2 decades now, usually in the study of compact relativistic objects or other relativistic phenomena. It's an especially key component of the detection and analysis of gravitational waves from mergers of compact objects. And so numerical relativity simulations of binary black holes merging, like this one shown here, give us these waveform templates that are consequently fit to our detections of these gravitational waves to infer properties of the system. And it's also used for simulations of merging neutron stars and is really vital in constraining properties of the equations of state of the neutron star from our observations. It's also used for other relativistic phenomena like supernova explosions and relativistic jets around accretion disks around black holes.
2 minutes.
And since about 2016 or so, this method has also been applied to simulations of inhomogeneous cosmology, which allow us to simulate a large-scale structure formation of the universe without needing to make any assumption of a global background spacetime, and really allowing our nonlinear matter field to interact with and talk to our underlying spacetime throughout its whole evolution. So this is still a really new field, so that means there's lots of interesting questions to answer. So this banner up the top here is showing a snapshot at redshift 0 of one of my simulations with numerical relativity, where you can see that you might notice it's slightly lower resolution than some of the cosmological simulations you're used to seeing. But the benefit of this is that we see the familiar cosmic web, but the good thing about these simulations is that we also have all of the information about the underlying space-time underneath this large-scale cosmic web and how it has interacted to form the structure that we see today. And so these simulations are extremely useful for testing the founding assumptions of standard cosmology, and as well as studying nonlinear general relativistic effects on cosmological observables, because we have the benefit of this framework, which is free from almost all of the assumptions made throughout standard cosmology. So please do keep an eye out for some exciting developments in this field, because we're really just getting started, and I'll leave it there. Thank you so much.
Thank you, Hailey. Any questions in the audience? Yes, you say your name.
Hi, this is Jose. Very, very cool. So I wonder, can you quantify the deviations that you expect? I mean, I see this picture and it looks, as you were mentioning, very similar to what we get from standard simulations. But where do you expect to see differences and how large you expect them to be?
Yeah, that's a really good question. So obviously people have quantified these kinds of effects using methods like perturbation theory. And there's even been some early work using these numerical relativity simulations, albeit in a regime that's not as nonlinear as this one I'm showing here, really just in the regime of kind of small perturbations. And even there, some of the effects you see, like some of the bigger effects are on weak lensing on large scales. They've showed that the power spectrum of weak lensing can be quite different when you consider nonlinear GR. There have been some works that have actually shown that the dynamics, and so the kind of the structure that you end up with between Newtonian and these full GR simulations is actually looks very, very similar. And so I kind of expect more of the differences to come up when you consider light propagation through this space-time, because then you're really capturing that your light is tracing the space-time. And so I think that's where kind of more of the effects are going to show up.
Anybody else? All right, let's thank Hailey again. Thank you, Hailey.
Okay, we have a coffee break now. Just have a couple quick announcements. Oh, and I can put the tours up. I know some of you, there's at least a couple of you that are writing NASA Keck proposals. They're due at 7 o'clock Eastern Time, 4 o'clock West Coast today. If you have any questions, please let me know. I'm happy to help. Well, I can't help right here. I'm happy to answer questions. And I want to put this up to remind everybody. So today's the last day for the Mission Operations Center tours. And if you haven't gone on one yet, hopefully your name is here. If it's not, if it is and you're not going for some reason, please let us know. Because I think there might be still a person or two that didn't get to go earlier and wants to go. And yeah, anyway. So remember, the group 7 will go at 1 o'clock, group 8 will go at 1:45. And then make sure if you're giving a talk tomorrow that you have uploaded your slides and or videos if you are remote to the Google Drive. And if you need that link, let us know. Thanks. We'll see everybody back at noon.